Hello everyone. In this video, we are going to learn about some nonlinear methods in computational statistics. The chapter for this text or this topic is chapter 7 of the ISLR textbook. So to begin with, the blunt story is that in the real world, relationships are rarely perfectly linear. And by relationships, I'm only talking about relationships in data, not anything else. While linear models give us a great starting point and offer wonderful interpretability, they make a fundamental assumption that the relationship that exists between our variables follow a straight line. But the reality is messy, complex, and often curved. When we plot real data, we frequently see patterns that bend, curve, or change directions. Think about things like diminishing returns in economics, or threshold effects in medicine, or seasonal patterns in time series data. None of these follow straight lines. So what happens when this assumption fails? Our predictions become biased, we miss important patterns in the data, and our inferences can become invalid. That is why we need more flexible approaches that can capture these nonlinear relationships. The good news is we can extend our modeling toolkit while still maintaining much of the interpretability, and that makes linear models so attractive. And throughout this lecture, we will explore some of these methods that strike a fine balance between flexibility and interpretability. Um, so, so, so when should we consider using nonlinear methods instead of sticking to the linear ones? That is an important practical question. Linear models continue to be incredibly useful when three conditions are met. First, when the relationship between our variables is approximately linear. Remember, models are simplifications, so close enough to linear model often works well. Second, when interpretability is critical, perhaps because you are in a field like medicine or policy, where explaining your model is as important as its accuracy. And third, when your data is limited. Linear models typically need fewer observations to estimate reliably. On the other hand, nonlinear methods become valuable in several scenarios. The most obvious is when your data shows a clear nonlinear pattern. Perhaps you have plotted your variables and see there are obvious curves or thresholds. And they are essential when you need to capture complex relationships that can't simply be approximated well using straight lines. Another scenario where prediction accuracy takes precedence over interpretability, maybe you're more concerned with getting the right answer than explaining it correctly how you got there. And finally, suppose you have enough data to run nonlinear methods. So obviously then you can use nonlinear methods. So in this video, we are going to go over some of the first cut nonlinear approaches. First, we have polynomial regressions, which is perhaps the simplest approach. Here we add polynomial terms like squared terms, cubic terms, and so on to our linear models. Think of this as allowing a regression line to curve by adding x squared, x cubed, and higher order terms. Next are step functions, which divide our predictors into discrete regions. This approach creates a series of steps in our prediction, allowing for sharp changes at specific thresholds. It is particularly useful when you expect the relationship to change at certain breakpoints. Splines are a more sophisticated version of step functions. They are essentially piecewise polynomials, but with continuity constraint at the boundaries. Splines give us the flexibility to model complex curves while ensuring smoothness where the pieces connect. Local regressions take a bit of a different approach. Rather than fitting one model to all data, they fit models to localized subsets of data. This allows the model to adapt to local patterns without being influenced by distant observations. Finally, we will explore generalized additive models, or GAMs in short, which combine multiple nonlinear functions into a single model. GAMs provide a powerful framework that preserves much of the interpretability of linear models while accommodating nonlinear relationships. What's beautiful about these approaches is that they offer flexibility while preserving much of the ease of interpretation that we value in linear models. Each has its strengths and appropriate use cases, and we will explore each of them in depth throughout this video. So let's start with the first one, polynomial regressions. This is perhaps the simplest way to extend linear models to capture nonlinear relationships. The concept is straightforward. Instead of just including our original predictor variable x, we also add polynomial terms of this predictor to our model. And in fact, you have done some version of that in your previous exercises. Therefore, our model looks like y equals beta naught plus beta 1x plus beta 2x squared plus beta 3x cubed plus dot 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 up to beta dxd, x to the power d plus epsilon. What is elegant about this approach is that we are still technically using a linear regression. I'm calling it linear because in the context of parameters beta, not the predictors themselves. We can fit these models using our standard linear regression tools after creating new variables that represent the polynomial terms. For example, if we have a predictor x, we can simply create new variables x1 equals x1 is x, x2 is x squared, x3 is x cubed, and so on, and just add them in a regression model. This means that we can use all our familiar linear regression machinery, least squared estimation, standard errors, hypothesis testing, which allow for curve relationships. It's just like giving our straight line the ability to bend and curve to match the patterns in the data. Implementing this in R is very simple. You can use the formula y tilde poly x comma degree 3 in the ln function to fit a cubic model. The poly function automatically creates the polynomial terms for you. One critical decision you'll need to make is selecting the appropriate degree. This choice represents an important trade-off between underfitting and overfitting your data. If you choose a degree that is too low, your model won't be flexible enough to capture the true pattern. And this is underfitting, which leads to high bias. On the other hand, if you choose a degree that is too high, your models will capture noise in your training data, and that is overfitting, which leads to high variance. And in this figure on the right, you can see how a polynomial fits of different degrees adapt to the data. The linear fit, which is of order 1, is clearly too rigid, while the highest order polynomial, order 5, might be capturing noise rather than just the true relationships. So how do we select the optimal degree? Cross-validation is typically the best approach. It helps us find that sweet spot that balances complexity with generalizability. Also, when interpreting polynomial models, focus on the fitted values and plots rather than individual coefficients, as the coefficients themselves can be difficult to interpret directly. Like any statistical method, polynomial regression has both strengths and limitations. So let's start with the strength. First, it is a simple extension of linear regression that most analysts already understand. It's easy to implement in any statistical software and interpret conceptually. We are just allowing our regression line to curve, that's all. Polynomial models are global, meaning they use all data points to estimate the parameters, which can be more efficient than local methods. They work particularly well for simple nonlinear relationships that allow smooth curves. And since we are still in the linear regression framework, we have access to standard errors, confidence intervals, and hypothesis testing. However, there are some limitations to be aware of. Polynomial models can behave poorly when extrapolating beyond the data. They tend to swing wildly in the tails. They are not locally adaptive, meaning they can't easily capture relationships that vary in different regions of the data. High degree of polynomials can be numerically unstable. Complex relationships might require many terms, making the model unwieldy. And like all global models, they can be sensitive to outliers. The bottom line is that polynomials are usually not the best approach for highly nonlinear data with complex patterns, but they provide a good starting point due to its simplicity and connection to linear models. They are often useful as a first step beyond linearity before exploring more sophisticated techniques. Now let's explore step function, a different approach to modeling nonlinear relationships. While polynomial regressions allow for smooth curves, step functions create discrete jumps in our predictions. The basic idea is to divide a continuous predictor into distinct regions or bins. Each region we estimate a separate effect. In the simplest form, we cut our predictor x into bins defined by the cut points, creating a series of indicator variables. So C1x equals indicator for x being less than C1, C2x is an indicator for x being between C1 and C2, and so on. And finally, the final cut, Ck, is an indicator for the value for all values of x greater than Ck minus 1. And therefore, our model becomes y equals beta naught plus beta 1 C1 plus beta 2 C2 plus beta k Ck. This approach allows the relationship between x and y to change abruptly at cut points. It is particularly useful when you expect threshold effects, where the impact of a predictor changes dramatically at certain values rather than smooth transitions. So this is what a step function looks like in practice. In this figure, we see a piecewise constant model with 4 categories: very low, low, medium, and high. Each region gets its own constant value, which means our function is discontinuous. It jumps at the boundaries between regions, and this approach is essentially equivalent to binning your data and calculating the mean response for each mean. The step function provides a simple but somewhat inflexible representation of nonlinear relationships. The real art lies in choosing the appropriate cut points, which we often call knots. There are several approaches to selecting these knots. You might use quantiles of your data distribution, incorporate domain knowledge about meaningful thresholds, visualize your data to identify natural grid points, or use cross-validation to optimize cut point locations. There is also a trade-off in how many regions to create. Fewer regions give you a smoother, more stable model, but can potentially miss important patterns. More regions create a more flexible model, but increase the risk of overfitting your model to the noise of the data. Notice how this approach creates a staircase-like pattern. While this may be crude compared to smooth curves, they can actually be advantageous in many fields where discrete categories are more interpretable, or where effects truly do change abruptly at certain thresholds. So now that we understand how step functions work, let's discuss some of the practical applications and limitations. Step functions have several strengths that make them valuable in certain contexts. First, they are exceptionally easy to explain and interpret. We can tell stakeholders exactly what happens in each category without complex mathematics. They are a natural choice when working with inherently categorical effects or when you want to create meaningful groupings. And they are particularly useful for modeling threshold effects where changes happen abruptly, like the minimum age requirements or income tax bracket or dosage response thresholds in medicine. You can also extend step functions to create interactions, for example, allowing the effect of age to differ before or after 2005 by creating a dummy for year being less than 2005 and interacting that with the age variable. This gives you flexibility to model more complex relationships. But step functions also have some limitations. The discontinuity at boundaries can be unrealistic for many natural processes, which typically change more smoothly. The information is lost when we bin continuous data. The results can be sensitive to exactly where you place the boundaries. The cut points can seem arbitrary without strong theoretical justification, and perhaps most importantly, step functions don't efficiently use all the information in your data. And these limitations naturally lead us to our next topic, which is splines, which offer a smoother alternative that addresses many of these shortcomings while retaining much of the flexibility that we want. Splines represent a significant advancement in our nonlinear modeling toolkit. They offer smoother alternatives to both step functions and global polynomials, combining the best aspects of each approach. At their core, splines are piecewise polynomials with continuity constraints at the boundaries. Like step function, they divide the predictor space into regions defined by knots, but instead of abrupt jumps, splines use polynomial segments within each region and ensure that these segments connect smoothly at the knots. This approach strikes an elegant balance between flexibility and smoothness. We can adapt to local patterns in different regions while maintaining a continuous function overall. This aligns much better with how most natural processes behave. There are several common types of splines, like a linear spline of degree 1 is the simplest form, joining straight line segments at the knots. Cubic splines, that is of degree 3, are cubic polynomials in each region for greater flexibility. And natural cubic spline add more additional constraints to improve behavior at the boundaries. So let's start with linear splines. Linear splines are continuous but not smooth. You will notice corners at the knots where the slope changes abruptly. Mathematically, with k knots at positions eta 1, 2 up to k, a linear spline model takes the form beta naught plus beta 1 x plus summation beta k plus 1 xi minus eta k. The notation, this difference over here, xi minus eta k, represents what we call a hinge function. It equals the max of this difference and 0. This means that the term is 0 when x is less than this value and equals this difference when x is greater than or equal to this value. This formulation results in the total of k plus 2 parameters or degrees of freedom. Each knot introduces an additional parameter that allows the slope to change at that point. Looking at the figure, you can see how the linear spline adapts to the data. Each segment has its own slope, allowing the function to change direction at each knot while maintaining continuity throughout that entire range. This offers more flexibility than a single linear function but maintains the simplicity of straight lines within each region. Linear splines are particularly useful when you want more flexibility than a simple linear model but need to maintain interpretability, as the slope in each region has a clear meaning. Cubic splines address this limitation, and by this limitation I'm referring to the limitation of linear splines being prone to abrupt changes. Cubic spline addresses this by using cubic polynomials in each segment that allows for smoother transitions. Cubic splines are more flexible than linear splines because they are piecewise cubic functions with important continuity constraints. They are continuous at each point, and their first and second derivatives are also continuous at each point. This means that not only the function connects smoothly, but the rate of change, which is the slope, and the curvature also transitions smoothly at the boundaries. This is the formula. This function creates a smooth curve that can adapt to complex patterns in the data. The higher degree of polynomials provide additional flexibility to capture nonlinear relationships, while the continuity constraint ensures a natural looking fit. However, this added flexibility comes with some challenge, and that challenge is in interpreting. Unlike linear splines, where a change in slope has a direct interpretation, cubic splines require us to focus more on the overall slope of the fitted function than the individual constraints. Natural cubic splines extend the cubic spline approach with additional constraints designed to improve the behavior at the boundaries. While regular splines or regular cubic splines are flexible, they can exhibit erratic behavior within, beyond the range of our observed data. And that problem is known as the boundary effects. Natural cubic splines address this by adding constraints that force the function to be linear beyond the boundary knots. Specifically, they require that the second and third derivatives equal 0 outside the boundary knots. These added constraint serves two purposes. First, they produce more stable estimates at the edge of our data range. Second, they reduce the total number of parameters needed. With k knots, the natural cubic spline requires only k degrees of freedom compared to k plus 4 for regular cubic splines. This more conservative behavior at the boundary makes natural cubic splines particularly suitable for extrapolation. When we need to predict beyond our observed data range, that's where this feature comes in more handy. But they are still flexible enough within the range of our observed data, making them an excellent choice for many modeling applications. An important practical question over here is how to choose the number and placement of knots. So how many knots should I have and where should I place them? That is a fundamental question. And this impacts directly the flexibility and performance of our model. So let's first consider how many knots to choose. This involves a familiar trade-off in statistical modeling. Too few knots lead to underfitting, and too many knots lead to overfitting. So right number balances these concerns. Once we have decided on the number of knots, next question is, where do we place them? There are several strategies that we can use. One approach is to have something like a uniform spacing across the range of my predictor, which means that I will place these knots uniformly throughout the range. Another common approach is to place the knots at the quantiles of the predictor distribution. This ensures more knots in regions with more data. If you have domain knowledge about where the knots should lie, you can strategically place knots at those locations as well. To select the right complexity of our spline model, there are several toolkits at our disposal. We can use cross-validation. It helps us find the model that will generalize best to the new data. Information criteria like AIC or BIC can also guide our selection by balancing goodness of fit with model complexity. Examining residual plots can also reveal where our model is adequately capturing the patterns of data, and sometimes a simple visual inspection can also help. Remember, the goal is not to find the true number of knots, rather select a model that is complex enough to capture the nonlinear effects, but not too complex that we end up inferring way too much. Smoothing splines offer a slightly different approach to spline models. Instead of manually selecting knots, smoothing splines automatically determine the right amount of smoothness using this function. Without going into the math, this function has two components. The first term, which is this, captures how well the function fits the data. This is similar to the sum of squared residuals. The second term penalizes the roughness of the function. So this here is the rough captures that, and this lambda over here is called the smoothing parameter. When lambda equals 0, there is no penalty for roughness. So the function will interpolate the data point exactly. As lambda approaches infinity, the penalty for roughness becomes dominant, forcing the function towards a more linear fit. The beauty of this approach is that simply by adjusting lambda, we can precisely control the trade-off between fit and smoothness. One interesting feature is, and in R, smoothing splines can be implemented in the smoothing spline function. You can control the complexity either directly through the degrees of freedom or by using cross-validation. One interesting feature of smoothing spline is that they automatically place knots at each unique x value and then use a penalty to prevent overfitting. This makes them very useful for exploratory data analysis when you're uncertain that the appropriate complexity is, is unknown. Next up is local regression. So the way this works is for each target point. So let's take a step back. The fundamental idea behind local regressions is very intuitive. Instead of fitting one global model to all your data, you fit simple models to localized subsets of your data. This allows the model to adapt local patterns without being constrained by one single functional form. Local regressions is particularly useful when the relationship between your variables is highly nonlinear and difficult to describe with a parametric function. Think of situations where relationship might be roughly linear in some regions, quadratic in others, and perhaps follow a completely different pattern elsewhere. Rather than trying to capture this whole thing with one complex function, local regressions help build many simple models that create a flexible fit. This approach represents a shift in philosophy from the methods that we have discussed so far. Instead of trying to specify the right functional form up front, local regressions let the data speak for itself, adapting to whatever patterns exist locally in different regions of your data. So let me walk you through the basic algorithm. For each target point x0, where we want to estimate the function, we follow these steps. First, we define a neighborhood around this point. Then we assign weights to nearby data points based on their distance from x0. Points closer to x0 receive higher weights because they are closer, and distant points receive lower weight or zero weight even if they are too far away. Next, we fit a weighted regression within this neighborhood, typically using a simple model like linear or quadratic regression. Finally, we use this local model to make a prediction at the target point x0. By repeating this process for many target points, we create a smooth curve that adapts to local patterns. The weight is calculated using this function. It's what we call a tri-cubic kernel. So the term h over here is called the span or the bandwidth. It determines the size of the neighborhood used for each local fit. This is a critical parameter that controls the smoothness of the resulting curve. This approach allows the regression function to change its shape across different regions of the data. It's like having a different model for each part of your data with smooth transitions between them. And if you look at these plots, you can see that the effect of different span settings in different local regressions. In the top left, we have the original data. With a small span of 0.1 in the top right, we are only using 10% of the data for each local fit. This creates a more wiggly curve that closely follows the data points, including potentially fitting to the noise. And as we increase the span, we end up having more smooth functions. The optimal span depends on your specific code. Whether you're more concerned with capturing fine details or you're more interested in identifying broader traits. In practice, cross-validation can help selecting an appropriate span, balancing bias and variance in your model. When implementing local regression in practice, there are some key parameters that you need to keep in mind. The first and the most important one is the span that determines the size of the neighborhood. It ranges from 0 to 1, represent what proportion of the total data is used for each local regression. Smaller span creates more wiggly fit that more closely follows the data. A larger span creates a smoother fit that might miss local features but is more stable. The degree parameter controls the complexity. Most commonly, we use degree equals 1 for local linear regressions or 2 for local quadratic regressions, but you can always ramp this up. The family parameter determines how outliers are handled. The default is Gaussian option that uses standard least squares, while the symmetric option implements a more robust version that is less sensitive to outliers. For any local regression model, selecting an appropriate span is crucial. You can manually set it, or you can let cross-validation decide for you. By testing different spans in the testing data, you can also identify the value that balances flexibility and stability. So local regressions, to sum up, offers a lot of strengths, but it's also not without its share of flaws. The strengths are it's highly flexible, it can adapt to almost any pattern in the data. It is particularly useful because you don't need to specify any function upfront, and it produces excellent visualizations that reveal underlying patterns. But the major drawback of local regressions is its computation. It can be computationally intensive, especially in a large data set, since it requires fitting many local models. It struggles with high-dimensional data due to the curse of dimensionality. What we mean by that is, as dimensions increase, neighborhoods become sparse. It doesn't provide a simple equation for the fitted function, making it difficult to summarize or communicate the relationship. It becomes less interpretable than parametric models. And because of these limitations, local regressions are often used for exploratory analysis and visualization than for formal inference. So the last one that we have in this video is GAMs. This represents a powerful synthesis of all the methods that we have discussed so far. The key idea behind GAMs is beautifully simple. Model the response as a sum of smooth functions of individual predictors. Mathematically, GAM takes the form y equals beta naught plus f1x1 plus f2x2 plus fpxp, where each fi is a smooth nonlinear function that is not predetermined. It is estimated from the data. Those functions can be splines, local regression fits, and other smoothing options. The advantage of this framework is that it preserves the additivity, which makes interpretation easy that we value in linear models. And this approach offers tremendous flexibility too. We can examine each function f separately to understand how that particular predictor relates to the response, holding other predictors constant. The first advantage of GAM is that it can capture nonlinear effects for each predictor without requiring you to specify the exact form of relationship. Despite its flexibility, GAM preserves the additive structure that allows for straightforward interpretation. You can visualize and understand the effect of each predictor independently, much like you interpret coefficients in a linear model. GAM also allows you to mix different types of components within a single model. You can include linear terms for some predictors, nonlinear smooth functions for the others, and categorical effects where appropriate. And this creates a modeling framework that is both flexible and practical. Most GAM implementations automatically estimate the appropriate smoothness for each function, removing the need to do it manually. And these properties make GAM a powerful tool to balance the flexibility. Here's an example. This figure has three panels. We see the effect of x1, which follows a linear pattern. In the middle panel, we see the effect of x2, which follows a sine wave pattern. And in panel 3, we see the effect of x3, which follows an exponential pattern. And because we are taking a GAM approach, we are allowing each of these predictors to retain its own relationship, and we are able to see that separately without disturbing the relationship between the response variable and the other predictors. So the way GAM works is that it is basically a sum of basis functions. Here beta j k are the basis functions, and what I mean by that is predefined functions that can be combined to create flexible curves, and beta jk's are coefficients estimated from the data. There are several common choices for these basis functions. Sometimes we go for natural cubic splines or smoothing splines or local regressions, and we control the smoothness by controlling the degrees of freedom as well as controlling the penalty. The model is then fit using a max penalized likelihood estimation technique. The nuances here is not that important, but it's useful to have this at the back of our head when you're coding it up. And this is and an advantage of that is that you can also naturally extend this to classification problems too. So in a classification context, rather than modeling the response directly, we model the log odds of the probability. This is similar to a logistic regression but with nonlinear components. And GAMs offer several advantages over logistic regressions. They can capture complex nonlinear effects that might be missed by nonlinear terms. This allows for more flexible decision boundaries that separate classes in your data. And importantly, they maintain component-wise interpretability. And here's a summary. So I summarize the methods and distinguish them in terms of flexibility and interpretability. And this kind of highlights the trade-off over here. Models that are high on flexibility are not that high on interpretability. And those that are high on interpretability are typically low on flexibility. So your job as a data scientist would be to find that sweet spot. So that's chapter 7. I hope this was useful. Please let me know if you have any questions. Thanks.